Alright, so in this video we're going to discuss electric potential energy in a uniform field. Now remember, work is the negative change of the potential energy. So in order to get the potential energy, we're going to be looking at work. And remember, work is essentially the force that is applied parallel to a displacement. So you have to push something, and whatever portion of force is parallel to the path you're taking leads to work being done. And just a quick aside before I go on, we can't forget about the conservation of energy. So while we're not introducing a new type of kinetic energy, we are introducing a new type of potential energy, but we can't forget about kinetic energy. So we are going to talk about particles in motion. And just a couple of sign rule reminders. Work is positive when force and displacement are in the same direction, and work is negative when force and the displacement are in the opposite direction. So your work is going to be positive if the force and displacement are in the positive x, for example, but the work would be negative if the force was in the positive x and the displacement was in the negative x. So in this case, we're going to talk about electric potential energy. So this is energy due to the electric force, the one we just learned about. So what I've drawn here is we have two plates of opposite charge, so positive and negative. And if we put a positive test charge here, the positive plate is going to push that positive charge away. The negative plate is going to attract it. And so we're going to see a force that pushes these positive charge towards the negative and away from the positive. And that's going to cause the charge to move over some distance d. So remember, work is force times displacement. In this case, the force is caused by the electric force. So we're going to take the electric field times the charge that is experiencing the force. Very similar to if this was a force due to gravity situation, we take the mass times gravitational field strength. So this is what we're subbing in here. So this means that work is the electric field strength times the test charge times the change in displacement. So potential energy would be Q, so the test charge, times the electric field strength times D. So because D would be that distance from the where we define 0 to be. Now keep in mind, this electric field is due to the other charges. So in this case, it would be electric field due to these two plates, not due to the test charge itself. So what this electric field is and how it's calculated is going to vary based upon what type of charge distribution is actually causing it. Alright, so in the second half of this video, we're going to discuss the electric potential energy due to a distribution of point charges. So I've drawn over here on the left sort of the idea of what is going on. We have some sort of charge Q we're trying to push along a path here, and there is another positive charge here. So the positive charge is going to push a force away from the point charge because they're both the same sign, so it's going to be a repulsive force rather than an attractive force. Now, in order for work to be done, the force and the path have to be parallel to each other. So what we're looking at is the component of our movement of our charge that is parallel to the force. So I'm going to label that dr. dl is going to be the original path it's traveling in. So in essence, we're looking at the idea that we're at some original distance from the charge and we're changing to some distance I'm going to call rb. That is a further radial distance away from the charge exerting the field. While at the same time, the charge is actually moving up and to the right. So we have the actual path versus the portion that is parallel to the force. And so the angle between there is phi. And so I've sort of set up this scenario where this is a right triangle. And this is important because dr, so this side of the triangle, is equal to the hypotenuse times the cosine of this angle. So this means that this scenario here depends upon r and not l. So it doesn't matter the actual path because the electric force equation doesn't have l in it, it has r in it. So I'm going to sub in to our work equation here. I'm first going to replace cosine of phi times dl with dr. And then I'm going to sub in the electric force equation, which is what I've done here. and then I integrate. So it turns out that work is a function of r to the first power, and thus potential energy, because remember work is equal to the negative of the change of potential energy, is a function of 1 over r rather than 1 over r squared. And I purposely have not drawn absolute value signs here, so you do now plug in the actual sign of the charge into the equation. So this is the relationship for calculating the work and the potential energy, essentially due to two charges. And you'll notice Q1 and Q2, you could just flip them, they're interchangeable. So potential energy is a shared property between two or more charges. You can calculate then the potential energy due to several charges on a test charge. So whatever charge you're labeling as Q naught. So that would be this charge in here. You can then calculate the potential energy it has due to a field of charges rather than just a single charge like you have up here, by essentially summing over Q over R for the remaining charges in the field. Q naught times charge 1, Q naught times charge 2, Q naught times charge 3, and then always dividing by the distance between those two particular charge sets. And if you want to be able to calculate the potential energy needed in order to assemble a field of charges, so if you want to know how much potential energy it took to get these charges here and this distribution from an infinite distance away, you would use this relationship down here. And once again, this is a summation because essentially you have to take each charge set multiplied together and then divide by the distance between them. And the reason why it says I less than j here is you don't want to take I times I or j times j, and you also don't want to have duplicate pairs. So if you take 1 times 2, you never want to take 2 times 1 because that's a duplicate. So this allows you to calculate the potential energy in different scenarios involving point charges. So if there's only 2 point charges, if you want to calculate the potential energy of one charge due to a bunch of other charges, and then the ability to calculate the potential energy due to assembling or placing a field of charges at a set of fixed spots, taking them from an infinite distance away into some sort of fixed assembly for a particular moment. Once you release these charges, they're going to start moving though, because of the electric force.